Great. Well, thank you all for being here. So you're all probably familiar with Python. In 2024, it became the most widely used language on GitHub. And a big part of the reason that Python is so popular is because it's very effective for gluing together calls to external libraries and other APIs. In this talk, I'm going to focus on scripts that glue together calls to large language models, because this is a particularly relevant and notable topic these days, but this work is actually fairly general. So to start off with what such a program might look like, consider this. So it's going to start off by making a call to a large language model. This is some kind of network request to get the cities in the Oceania region of the world. Maybe I'm trying to book a vacation or something like that. And so language models are slow, so this might take 5 or 10 seconds to execute. Say it takes 9 seconds. And then I get back this list containing Honolulu and Brisbane. So next, we're going to loop first with the city Honolulu, and we're going to make another LLM request, so again, another network request, to get some fun excursion I could do in that city. And maybe I get back a while later, because LLMs are slow, that in Honolulu there's scuba diving. So next, I'm going to print this to standard output. And in this case, it took 17 seconds. I'm going to call this time till first print, the latency of the program. And then continue executing. I'll do the loop again. Again, there's a slow LLM call. I hear back something about koala sanctuary in Brisbane. And after 21 seconds, the program is done executing. So something like this might be a simple program, but it's sort of illustrative of a sort of emerging workload of compound AI systems. And so if you look at the machine learning literature, people are publishing lots and lots of stuff that sort of crudely boils down to making a bunch of calls to LLMs that get stitched together in various interesting ways. Of course, making external API calls is kind of the hallmark of scripting. It's what makes scripting what it is. But there's something special about LLMs, which is that they're excruciatingly slow. So something you noticed here is that the performance bottleneck of this script was the external calls. So I spent basically no time executing the for loop for a couple iterations. But instead, I was waiting for these LLM calls to get back to me. So if I wanted to improve performance of something like this, how could I do it? Well, one way would be through parallelization. So I had these two get excursion calls for Honolulu and Brisbane that were independent. So ideally, I do them in parallel, and that would reduce the running time of the program. Another way I can improve the performance is through streaming. So in particular, LLMs are slow to produce their entire output, but they actually produce it incrementally and very quickly get the first token. So maybe after 3 seconds, I get Honolulu, and after 3 more seconds, I get Brisbane. And it's only after 9 seconds that I get the end of stream token. So in this case, what I might like to do is after 3 seconds, dispatch my get excursion call for Honolulu. After 3 more, dispatch for Brisbane. And if I could do this, I would dramatically reduce the running time of my program. Of course, parallelization and streaming are complicated. So if I start with this very simple program, and then parallelize it using Python's async machinery with futures, I end up having to split my for loop into 2, where the first for loop ends up handling the futures, and the second for loop ends up handling the values. And this is adding complexity, but this is just if I'm parallelizing. If I'm also streaming, it gets a lot more complicated. It's like 50 lines of code, and when I did this, I actually had a deadlock that then took me a while to debug. And so a natural proposal is well, what if we could solve this problem by just doing parallelization and streaming automatically? That would be great. Now, this is something people have wanted for a long time, of course. It's not exactly a new idea. So for automatic parallelization in particular, there's been a lot of work that focuses on sort of systems code. But systems code, written in a language like C, is really qualitatively very different from glue scripts written in a language like Python. So one key difference is that in systems code, most of the work is happening in your program itself. You're doing hard computational work. Whereas in a Python script, you're typically doing most of your hard work in external API calls, not in the program itself. In systems code, parallelization has overhead, and that overhead ends up being significant. Whereas in glue scripts, you're sort of not worrying about overhead anyway, and so you might not have to worry about overhead so much. Systems code tends to rely heavily on mutating data structures that live on the heap, whereas glue scripts, often you really don't end up with any kind of complex heap manipulation. And lastly, systems code tends to be compiled, whereas glue scripts tend to be interpreted. And this is a key difference that is going to let our approach work, because we're basically proposing an alternative evaluation strategy for scripts. So to return to our example, as before, we're going to do our get cities call for Oceania. But rather than waiting for the result to get back, we're going to dispatch it. We're going to send off the network request, and then we're immediately going to replace the call site with a hole, which here I've called A0. And And then what we're going to do is we're going to continue executing. We know that cities is A0, and we have an occurrence of cities. So we can reduce, basically just do an ordinary reduction in something like lambda calculus, but treating the holes as some kind of atomic value. So we can do this substitution. And now we get stuck. There's nothing we can do until we know something else. But maybe after 3 seconds, we get Honolulu back from the LLM. So in that case, we're going to do what I'm going to call a resolution step, where we take our hole, A0, and we replace it with something, some term that may contain other holes. And in particular, we're going to replace it with the list containing Honolulu concatenated with another hole, in this case, A1. But then what does this buy us? Well, we're looping over a list where we know the prefix of the list. Why don't we just unroll this? And so, in fact, reduction will unroll it. And then we'll see that city is Honolulu, so we can substitute. And then, well, we have another external call with a concrete argument. Why don't we just dispatch this now? Well, that's exactly what we're going to do. So we're going to dispatch it, and again, send off the network request and replace the call site with a hole, in this case, B0. So we can continue to do a little bit of evaluation, but very quickly we get stuck. But now we're waiting for one of 2 large language model calls to get back to us. So maybe we wait a little while, and we actually hear back in Honolulu something happens. So again, we replace B0 with a string concatenated with another hole. But now we have a print statement where we know the prefix of the string that's being printed. Why don't we just evaluate that now? So in fact, we're going to do that. Maybe we wait a little while longer. Or, oh, I should say, like here, we've been able to print something to the user much, much more quickly than we were able to before. So we wait a little while longer. Maybe we hear back Brisbane is a city. So as before, we're going to replace the whole A1 with the list containing Brisbane concatenate another whole A2. Again, we can unroll our loop. Again, we can substitute. And again, we can dispatch our Brisbane call. So maybe we wait a little longer. We hear back that in Brisbane, you can do something. It has something to offer. Now, before I said we could print. But if we were to print here, we would be kind of interleaving our 2 print calls. So that's unsound. It's not something we can do, but that's OK. It's the best we can do. But maybe we wait a little longer. We get back the end of stream token. So the whole A2 gets replaced by the empty list. And now if we're looping over the empty list, we can just step that away. Maybe again, we hear back on Brisbane that it has a koala sanctuary. And I said, well, we couldn't print because printing is order sensitive. But there are other operations that aren't order sensitive that we might be able to do. Like in this case, string concatenation. So if we concatenate these strings, we can make a little bit of progress. So maybe finally we hear back on B1 that people enjoy scuba diving. So now we're going to be able to finally do this print. But then our last print statement is ready to go. We don't have to do any additional work before we can dispatch it. So this is sort of an illustration of how our approach works. But at its core, it consists of a core calculus called opportunistic lambda calculus. It's a lambda calculus, but with first-class support for non-deterministic, i.e. impure, external calls. The semantics allows execution in arbitrary order. There is a key assumption, which is that external calls don't have hidden state. But this actually doesn't limit us. Because if there is state that external calls need, it can be threaded from one call as an argument to another call. We have a theorem, which is confluent, which basically says that the order in which we do this evaluation doesn't affect the final result. And a corollary of this is soundness, that any order in which you do evaluation is going to match a sequential evaluation, at least for terminating programs. So there are a few challenges. One is the evaluation strategy that we should actually choose. We had this non-deterministic, we can do things in any order, but what order should we choose? If you consider this program that loops forever, and then prints foo, and then returns an LLM call, strict evaluation would get stuck looping forever. Lazy evaluation would return the LLM call, but it would never do print, because that's not really required for the output. So we actually have a non-strict, non-lazy strategy we call opportunistic, which is sort of going to do all 3 things, and in particular, it's going to print. Another challenge is how to actually represent the partial data that I was showing before. So if you imagine you have 2 streams, one that's in Honolulu something, and the other is Brisbane offers something, and you concatenate them, you end up with some kind of partial string that has a hole in the middle. And it turns out that algebraic data types are not very good at representing things like this, and so we actually use church encodings in this work to represent this kind of partial data. If you're interested in more details about this, I'd be happy to talk about it or take a look at our paper. We implemented this, and it's available on GitHub and also has been evaluated. We implemented our core calculus, Lambda O, with a small step operational semantics, so it really does evaluate, much like I showed you in the example. On top of it, we implemented a scripting language called Opal that has structured control flow and automatic streaming. And all of this is embedded in Python. So code is written in a subset of Python. And then currently, we're actually extracting Opal terms from Python using symbolic execution. Additionally, external calls in the language are just calls to external existing Python libraries. We did some experiments on 5 benchmark programs that we pulled from the LLM literature. We measured the latency, the time until the first output, and the total running time, the time until the last output. And first, we compared to sequential blocking Python implementations of each of these benchmarks. And we found that we got significantly better latency and significantly better running time, which should be unsurprising. We also compared to manually parallelized asynchronous Rust implementations of each benchmark. And this is sort of the best performance you could reasonably hope to get. And while there is some overhead, the overhead is relatively modest, particularly considering that we're doing a small step operational semantics for our implementation. And finally, we compared to several baselines for parallelization and streaming. We compared to Bash, Pash, Apache Flink, and SGLang. SGLang is actually an LLM-specific framework. And we found that we got better latency, better running time, or both. So to conclude, we contribute a core calculus, Lambda O, that has first-class support for impure external calls, a parallel evaluation strategy that automatically extracts parallelism, but is able to match the semantics of sequential evaluation. We built on top of this a scripting language called Opal, which is embedded in Python, and it offers structured control flow and streaming. And we evaluated on 5 benchmark programs. We found that we got significant speedups and relatively low overhead. So finally, existing scripting languages are high level in that they automate certain low-level details like memory management. And I think that future scripting languages can and should automate low-level details like parallelization and streaming as well. If this is something you're interested in, or you're also interested in the broad field of language design for large language models, I am looking for a postdoc position. So if you or anyone you know is interested, please let me know. And I'd be happy to take your questions.
Hello? Yeah. Well, thank you for the talk. There's something that bugs me a little bit in the example you showed us, is that because you print part of the first strings, you have to wait for the second one. Whereas as a user in that case, anyway, I don't care whether I get the information for one city before the others. So is there a solution so you just wait and put them in different order, but then...
Yeah. I think it's essentially an API design choice of whether you're printing a list of strings or a bag of strings. And so, I mean, I think my answer would be that these are really 2 separate functions. There's kind of print in order and there's print out of order.
Okay.